Hi everyone. Today in this video we are discussing the molecular orbital theory of covalent bonding. Before that, let's look into the previous video discussions. We have already seen an introduction to chemical bonding, the details of ionic bonding, and also some concepts of covalent bonding. That is the valence bond theory of covalent bonding. And we know, according to valence bond theory, a covalent bond is formed by the overlapping of half-filled atomic orbitals of the combining atoms. But in molecular orbital theory, it is a more quantum mechanical approach. We know, according to quantum mechanics, the electrons are assumed to be having dual nature. That means in addition to particle nature, they have wave character also. And we know, associated with each wave, there will be a wave function. So, according to molecular orbital theory, here also the covalent bond is formed by the combination of atomic orbitals, but the wave functions of atomic orbitals are actually undergoing combination here in molecular orbital theory. So we can say, according to molecular orbital theory, a covalent bond is formed by the combination of wave functions of atomic orbitals. So now let's take the example of a covalent bond formation by molecular orbital theory. For a compound, let's say a diatomic molecule of the type AB, and let psi A be the wave function of atomic orbital of A and psi B be the wave function of atomic orbital B. So according to molecular orbital theory, a covalent bond is formed by the combination of these two atomic orbital wave function. So we can say a molecular orbital will be formed. It can be formed by the addition or by subtraction. That means the combination can be either by addition or by subtraction. So we will get two molecular orbitals. So that means, according to molecular orbital theory, the number of molecular orbitals formed will be equal to the number of atomic orbitals combining. Here psi A is the atomic orbital wave function of A and psi B that of B. So two molecular orbitals are formed by the combination of two atomic orbitals. One molecular orbital which is formed by the addition of the wave functions, and that is called the bonding molecular orbital, represented by the symbol psi MO. And the other one is formed by the subtraction between atomic orbital, and that molecular orbital is termed as anti-bonding molecular orbital, which is represented by the symbol psi star MO. So psi MO represents bonding and psi star MO represents anti-bonding molecular orbital. So this type of combination of atomic orbitals to form molecular orbitals is called LCAO approach. LCAO means linear combination of atomic orbitals. Linear combination of atomic orbitals is called LCAO approach. That means, according to molecular orbital theory, a covalent bond is formed by the overlapping or by the combination of atomic orbital wave functions, either by addition or by subtraction, resulting in two molecular orbitals. One is termed as bonding molecular orbital, that is by addition of a wave function, and the other molecular orbital formed by the subtraction of atomic orbitals is called anti-bonding molecular orbitals. So this type of combination of atomic orbitals is termed as LCAO, linear combination of atomic orbitals. And here it is by addition. So this is in phase, or we can say this combination is in phase and it is stabilizing. So the resulting molecular orbital is a stable bonding molecular orbital, and that will have a lower energy than the atomic orbitals. Than the atomic orbitals A and B, whereas the psi star MO is formed by out of phase combination. It is subtraction, no? So the wave functions are combining out of phase, and hence the resulting molecular orbital or the anti-bonding molecular orbital will have higher energy than the combining atomic orbitals. So we can generally say two atomic orbitals combine to give two molecular orbital. One will be having lower energy than the atomic orbital, which is bonding molecular orbital, and the other one will be having higher energy than the atomic orbitals, which is termed as anti-bonding molecular orbital. And this type of combination is called linear combination of atomic orbitals. Valence bond theory and molecular orbital theory both stem from the same concept. That means covalent bond formed by the atomic orbital combination. But there are some differences also. According to valence bond theory, the atomic orbital concept is retained even after bond formation. Whereas in molecular orbital theory, once the atomic orbitals have combined to form molecular orbitals, the resulting orbitals won't have the characteristics of atomic orbital. Or we can say the molecular orbitals will have different energy and different shapes. Okay, so that is the main difference, and the electrons are now filling in the molecular orbitals in the order of their energies. So all the rules of electron filling in atomic orbitals are obeyed by molecular orbitals also. That means they obey Aufbau principle. Aufbau principle states that electrons are filled in the orbitals in the increasing order of energies. So here also the molecular orbitals, the electrons are filling starting from the lowest energy molecular orbital to the highest energy one. And also it obeys Pauli's exclusion principle. That means no two electrons in an atom can have the same value for all four quantum numbers. And also the Hund's rule. Pairing of electron will not take place as long as there is a vacant orbital of the same energy. So when we have two or we can say when we have two degenerate energy levels or degenerate orbitals, electrons are first singly occupied in them, and then only after singly occupying only it goes for pairing. So all these rules of electron filling are obeyed by molecular orbitals also. Now let's see how different molecular orbitals are formed. So let's start with the lowest energy atomic orbital, 1s. So the two 1s atomic orbitals, how they combine, or what change in shape and energy take place when the two 1s atomic orbital combine to form a covalent bond, as in the case of hydrogen molecule, say for example. So the 1s atomic orbital, we know the shape of 1s atomic orbital is spherical. It is having only one side. It is uniform in electron density, is uniform in all direction. So this 1s orbital can combine with another 1s orbital in two ways, either by addition to give bonding molecular orbital or by subtraction to give anti-bonding molecular orbital. So we can say the two will add or two will combine by addition to give a bonding molecular orbital, or the 1s and 1s will combine by addition, by subtraction to give anti-bonding molecular orbitals. Okay, so we know this is the bonding molecular orbital that is formed by the addition of atomic orbital, which is represented as sigma 1s, and the molecular orbital formed by the subtraction of atomic orbitals is called sigma star. We know this is a sigma bond, atomic, the 1s and 1s, or we have already seen in the previous video that s orbitals combine in a head-to-head manner to form a sigma bond. So here the two 1s atomic orbitals are formed by addition to give a sigma molecular orbital, and hence it is termed as sigma 1s, whereas the atomic orbital combined by subtraction. So here it is the positive side. They combine by subtraction to give the sigma star 1s, anti-bonding molecular orbital. And we know obviously sigma 1s is having lower energy than sigma star 1s. Okay, so this is how bonding and anti-bonding molecular orbitals are formed by the combination of 1s and 1s atomic orbital. So after 1s, we know it is the 2s atomic orbital. They also having same symmetry as 1s only the energy is different. So the 2s and 2s combine in the same way to give a orbitals of same shape but with slightly higher energy. So we can say 2s atomic orbital combined by addition to give sigma 2s. We can represent it in this way, sigma 2s with 2 electrons, and they combine by subtraction to give sigma star 2s. Okay, so this is the combination of 2s atomic orbitals combined by addition to give sigma 2s and combined by subtraction to give sigma star 2s, and we know sigma 2s is having lower energy than sigma star 2s. So this is the formation of molecular orbitals from s atomic orbital. 1s combined to give sigma 1s and sigma star 1s, 2s combined to give sigma 2s and sigma star 2s. The next higher energy atomic orbital is the 2p. After 1s and 2s we have 2p atomic orbital. And we know in the 2p subshell we have 3 orbitals which are labeled as 2px, 2py and 2pz. In the previous videos we have already seen that the z axis is assumed to be the internuclear axis, and hence the orbital lying along the z axis can combine in a head-to-head manner to form sigma bonding. So here what happens is the 2pz, we know px, py and pz are the 3 p orbitals. Px is lying along z axis, dumbbell lying along x axis, py is along y axis and pz is along z axis. Okay, so here only the pz atomic orbital is lying along the internuclear axis and it can combine head to head with another pz atomic orbital, whereas px and px, their geometry does not allow any sort of head-to-head interaction. Rather, they combine in a sidewise manner to form pi bond. Similarly, py with another py combine to give pi bonds. So first of all, let's take the pz case. So here we know, even though the p atomic orbitals are having same energy, the molecular orbitals formed from them are having different energies. That is because of the difference in orientation or difference in the type of covalent bond formed. One will form sigma bond, whereas the other 2 atomic orbitals form pi bonds. So first of all, let's take the combination of 2pz atomic orbitals. So 2pz atomic orbitals combine to give 2 molecular orbitals. That will be sigma 2pz and sigma star 2pz. They can combine by addition to give sigma 2pz that is by addition, or the atomic orbital wave functions combined by addition to give a bonding molecular orbital which is labeled as sigma 2pz, and they can combine by subtraction. Combination by subtraction give anti-bonding molecular orbital. So that is labeled as sigma star 2pz. So 2 molecular orbitals are formed, that is sigma 2pz and sigma star 2pz, formed by the head-to-head interaction. Now let's take the px and py sets. So the 2px and 2px will combine by addition to give the pi 2px, and they combine by subtraction to give the pi star 2px. So the 2p, this is the shape of the px atomic orbital. 2px and 2px combine to give, or they combine by addition to give pi 2px bonding molecular orbital, and they combine by subtraction to give pi star 2px anti-bonding molecular orbital. We know whenever there is star symbol, that represents anti-bonding and which will be having higher energy than the bonding molecular orbitals. So in the same way, the 2py and 2py combine to give pi 2py and pi star 2py. So this pi bond is formed in the same way for 2px and 2py. So we can say the pi 2px and pi 2py are having same energy, and their corresponding anti-bonding will have same energy. Okay, so pi 2px and pi 2py are having same energy. The same way pi star 2px and pi star 2py are having same energy. Among the two sets, we know the bonding will be of lower energy than the anti-bonding molecular orbitals. So we have discussed the different atomic orbital combination to give molecular orbitals, their shapes and energies. Now let's see how is the order of energy of different molecular orbitals. We have seen the combination or molecular orbital formation from 1s, 2s, 2p, etc. So the order of energy of these molecular orbitals we can see now. When we write the energy order of molecular orbitals, actually there are two sets of energies, or there are two types of configurations for up to 14 electron and greater than 14 electron systems. Up to 14 electron in the sense the total number of electrons in the molecule. If it is up to 14, there will be one configuration, and if the total number of electrons is more than 14, there will be a different configuration. So first we see up to 14 electron system. That means, like for example, nitrogen, carbon monoxide, etc. These are having 14 electron, and also we can also write MO configuration for B2, C2, etc. So for them the order is sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than pi 2px equal to pi 2py less than sigma 2pz, which is less than pi star 2px equal to pi star 2py less than sigma star 2pz. So this is the order of energy of different molecular orbitals. So molecular orbital configuration for up to 14 electron system. That is, first we have sigma 1s, then sigma star 1s, the bonding and its corresponding anti-bonding, then sigma 2s and its anti-bonding, and after that the pi 2px and pi 2py. Then only the sigma 2pz, then pi star 2px, pi star 2py, and finally sigma star 2pz. And this order exists because in the case of smaller electronic system, like up to 14 electron system, the number of electrons is less, so the energy difference between the 2s and 2p is very low, and this low energy difference causes an increased interaction between the 2s and 2p. So for example, in the case of nitrogen molecule or up to 14 electron system, the 2s atomic orbital and 2p atomic orbital energy difference is very small. So there will be a large extent of interaction between the two atomic orbital. And this interaction, this sort of interaction raises the energy of the sigma 2p cell. Actually, usually we expect after sigma star 2s, sigma 2pz should come. But in the case of the smaller electronic system, there is an increased interaction between 2s and 2p atomic orbital, and this interaction raises the energy of the sigma 2pz. Whereas in the case of higher electronic system like fluorine, oxygen molecule, etc., in these molecules there is this energy difference is more, so no such interaction, no interaction between the 2s and 2p atomic orbital, because like in the higher system there is not much interaction between these two because their energy difference is more, whereas in lower electronic system the energy difference between these two are very less. So this will interact, and that interaction raises the energy of sigma 2pz. Okay, so anyway, let's see, just remember this difference alone. That means for up to 14 electron, this is the case, and for more than 14 electron, there will be one difference, only one difference is there. After sigma star 2s, the sigma 2pz come. Then only pi 2px and pi 2py. That means the position of these two molecular orbitals, this one and this set will be interchanged. That means sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than sigma 2p z. So after this, after sigma star 2s, there comes sigma 2p z. Then only pi 2px equal to pi 2py. Then pi star 2px equal to pi star 2py. And finally sigma star 2pz. So this is the order for more than 14 electron system like F2 and F2, O2, etc. So for this case, this is the order. That means only this thing you should remember. After sigma star, in the case of 14 electron system, up to 14 electron system, after sigma star, the pi 2px and pi 2py come. Whereas for more than 14 electron system, after sigma star 2s, the sigma 2pz will come. So this is the order of energy of different molecular orbital, or we can say MO configuration for different molecules. So based on this, we can write the MO configuration of different molecules. First of all, we have to count the number of electrons in the molecule. So you must know the atomic orbital configuration. So when you take a diatomic molecule like nitrogen, we know nitrogen atom is having 7 electrons, and so nitrogen molecule which contains 7 plus 7, 14 electrons. So if you know the total number of electrons, you can fill electrons according to any of these two configuration. If it is up to 14 electron, this configuration works, and based on that you can write down the MO configuration. So after writing the MO configuration, we can predict many factors in a covalent bond, or many things about the molecule we can predict using this MO theory. So those things we can discuss in the next video. Okay, so in this video we can cover up to the molecular orbital configurations of different molecules. Hope you all understood this. Thank you.